This is part 2 of lecture 8 of Logika računalništvu. In part 1 we started the LTL model checking problem. We stated what that problem is, and we began looking at how to solve the problem algorithmically. And to do that, we introduced the notion of Bookey automaton and the related and slightly more general notion of generalized Bookey automaton. In this part, we're going to put these Bookey automata to good use, but we're not going to complete the algorithmic solution to the model checking problem. That's going to be done in a third part, which will be the first part of the lecture next week. So far we've met Bookey automata, which have these graphs with these initial states and accepting states, and they define a so-called omega language of infinite words. This one defined the empty language. And then we have the generalized non-deterministic Bookey automata that only differed by they had not just one set of final states, but potentially more sets of final states. So this particular one had two sets of final states, both singleton sets, and the acceptance condition for the automaton was defined using the different sets of final states. So generalized Bookey automata are a little bit more general. Obviously, every ordinary non-deterministic Bookey automaton is a generalized one. You just simply have one set of final states rather than more than one set of final states. So did we really need to introduce the generalized non-deterministic Bookey automaton? Well, in some sense, no, because we have the following result, which I shall state, and it will be an exercise in exercise classes to prove it. So the proposition is that the following are equivalent for a set of infinite words. For a set L, let's say, which is a set of infinite words, so it's a subset of the set of all infinite words over some given alphabet sigma. So the first statement is there exists a non-deterministic Bookey automaton A that recognizes exactly this set of words, so such that this set of words is the language of omega words accepted by A. It turns out that that's equivalent to there exists a GNBA A, such that L is the set of omega words accepted by the generalized non-deterministic Bookey automaton. So I'm not actually going to prove it here, I just want to make some notes about it. So one direction is easy, that if there exists a non-deterministic Bookey automaton A such that L is the language of that non-deterministic Bookey automaton, then there certainly exists a generalized non-deterministic Bookey automaton, because any non-deterministic Bookey automaton, any ordinary one, is a fortiori a generalized one. You just simply have one set of final states. A generalized non-deterministic Bookey automaton can have one set of final states, or it can have more than one set of final states. So 1 implies 2 is easy because generalized non-deterministic Bookey automaton, like their name suggests, really do generalize non-deterministic Bookey automata. 2 implies 1, is not easy, but it's not terribly difficult. So suppose we've got a generalized non-deterministic Bookey automata that accepts a language, that recognizes a language L, or recognizes the set of infinite words L. Well then, how can we prove 1? Well, what you need to do is you need to cleverly construct an ordinary non-deterministic Bookey automaton that accepts the same language. And that's going to be an exercise for exercise classes. So it's an interesting exercise, how to construct the generalized non-deterministic Bookey automaton. So in some sense, we didn't really need to introduce generalized non-deterministic Bookey automata, because we could whenever you can use a not generalized one, you could get away with a normal one, an ordinary non-deterministic Bookey automaton. But that ordinary one will typically be more complicated. So actually it is going to be useful to have the generalized ones, because that allows us to give less to use less complicated automata in the constructions, generalized automata in the constructions, than we would otherwise use. Right, so it turns out this notion, when is a set of infinite words, we shall call the set of infinite words a language, like a language in some sense is a set of words, like the Slovene language is in some sense the set of all Slovene words. Of course, there's much more to it than that, and the English language is kind of the set of all English words. So this is a very simple idea of a language, but anyway, so here we're going to have an omega language is a set of infinite words over an alphabet, and so as we can see, that it's an interesting property for a language. Does there exist a non-deterministic Bookey automaton that recognizes the language, or equivalently, does there exist a generalized non-deterministic Bookey automaton that recognizes the language? So what we're going to do is make a definition that a set of infinite words subset. So a set of infinite words, that's a subset of the set of all infinite words, a language, or let's say an omega language, actually let's call, this is part of the definition, a set L is called, oh dear, let's rewrite this a bit. So we call sets of infinite words, in general we call them omega languages. Omega because the words are infinite. So an omega language, that is a set of infinite words. An omega language L is said to be omega regular if there exists a non-deterministic Bookey automaton such that L is the omega language of the non-deterministic Bookey automaton. So basically, an omega regular language, omega language, but one doesn't need to repeat omega too many times. So an omega regular language is a language that is recognized by a non-deterministic Bookey automaton, or equivalently by the proposition, a language that is recognized by a generalized non-deterministic Bookey automaton. And proposition is that if L1 and L2 are omega regular, both over the same alphabet, then so are their union, their intersection, and their complement. Well, the complement of either of them. So let's say sigma to the omega, so all the words in sigma to the omega not in L1. So these again are going to be, or these the first two are going to be exercises. So this one you prove using NBAs. So it's an exercise. So the idea is you've gotten an NBA that recognizes L1 and you've got an NBA that recognizes L2, and you need to construct one that recognizes L1 union L2, that recognizes the union of the two languages. So exactly the omega words that are in either one of the languages. This one, the intersection, you need to recognize the omega words that are in both languages. This one you prove using GNBAs, generalized non-deterministic Bookey automata. So again, I'll leave that as an exercise. So it's much easier to prove this using generalized non-deterministic Bookey automata. And this one, closure under complement, well, anyway, we're not going to need it, but this is a deep result due to Bookey. And just to say, his proof used the infinite Ramsey theorem. It's quite an intricate combinatorial proof, so I will not set that as an exercise, but this is a beautiful result, but we're not going to need it, so we shall not look at it. Okay, so we have two different tools for recognizing omega languages, non-deterministic Bookey automata and generalized non-deterministic Bookey automata. Both are equivalent in power. In general, the generalized ones are a little more convenient to work with. For example, to prove this statement 2 here, the closure of omega regular languages under intersection, and we are going to now use generalized non-deterministic Bookey automata to work further towards addressing the model checking problem for LTL. Right, so let's go to a new page. So what we're going to look at next is something called the trace language of an LTL formula. So to motivate this, let's suppose we've got two runs. Remember, a run, or two runs through a transition system, or even through two different transition systems. So remember, a run is basically what you think it should be. It's sequence of states where from each state you make a transition in the system to the next state. So it represents an execution path, as you like, if you like, of the transition system. So let's suppose we consider two different runs. So let's call the first one I think I was numbering from 1 last week, so let's do that. So S1 to S2 to S3 to S4. So this is one run. So runs, remember, are infinite, or infinite paths, I maybe was calling them last week as well. So this is in a transition system M. And let's say we've got another run, which could be in the same transition system, but doesn't have to be. It could be in a different transition system. So this is in potentially in a different transition M prime. So these are two potentially, they don't need to be different, different transition systems. And suppose these two runs enjoy the property. So suppose also that these two runs enjoy the property that the set of propositional atoms labeling each state Sn is the same as the set of propositional atoms labeling each state S prime n. So that for all n, so I think we called it L, the labeling function. So L of the state Sn is the same as the L of S prime. This is an n of S prime n. Maybe I'll write that n a bit more clearly too. So the point is we have two runs, and at every corresponding pair of states, so we have the starting states, so that's the corresponding pair, so that if you like, the states at time 1, the states at time 2, the states at time 3, for every such pair of states, exactly the same propositional atoms are true. So remember, propositional atoms were things like, in the examples last week, process 1 is non-critical, or process 2 is trying to get critical, and things like this. And so we've got exactly the same propositional atoms true, and hence exactly the same false as well at each of the pairs of the corresponding pairs of states. So within each oh dear, I'm getting into a mess here. So for each pair of corresponding states, exactly the same propositional atoms are true. That's what it says here. So then it follows that for all LTL formulas phi, that the first path, let's call it pi, that the first path satisfies phi if and only if the second path, so let's call that pi prime, moreover, not only does it hold for the whole paths themselves, But it also, the same property also holds for the shifted paths. Remember, we were writing pi superscript 2 for the path where we start, where we can consider the subpath starting from state 2, pi superscript 3 for the subpath starting from state 3 and continuing state 4, and so on. So we could also say, and for all n, that pi of n, so this was the notation from last week, and pi prime of n. So what this equivalence is saying is that the truth of formulas of LTL does not at all depend on the identity, the precise identity of the states we go through. It really just depends on the sequence of properties that hold at the states. So we have a run, it goes through an infinite sequence of states, and the truth of LTL formulas just depend on the sequence of the sets of properties that hold of those states. That's not very surprising, but it's a nice fact, and what it allows us to do is to define something called the trace language of a formula. So one way of summarizing this is that, so whether or not a path pi or run, remember I was using paths and runs equivalently last week, so let's put paths there just to keep the terminology the same. So whether or not a path pi satisfies a formula phi depends only on the trace of the path, where the trace of the path is the function that maps each index for an element of the path n to the set of atoms labeling the nth state in the path. Or equivalently, we're actually going to view it as, so this we're viewing it as a function, I've written it as a function here, or equivalently, we can view the trace of pi as an omega word, so that's an infinite word, over the alphabet the power set of atoms. So that is the alphabet. The symbols we use for the words are sets of atoms. So the power set of atoms is the set of all subsets of the set of atoms. So the symbols are sets of atoms. And so we can view it as an omega word because the omega word is the first symbol is L of S1, the second symbol is L of S2, the third symbol is L of S3, the fourth symbol is L of L of S4. with symbol Alabas 5 and so on. So that's first. So this is the first symbol in the omega word. The second symbol. Third symbol, etc. Okay, so every path has a trace, namely the sequence of the sets of atoms true at the respective states in the path, and whether or not an LTL formula is satisfied by the path depends only on the trace of the path. So what we're going to do is define the trace language. So we're going to define the trace language of an LTL formula. Oops, let's go back to black. So this is going to be, I'm going to call this traces phi. So this is going to be a set of, so it's going to be a set of infinite words over the, alphabet given by the power set of atoms. So indeed, so it's a set of infinite words where each individual symbol in the infinite words is a set of atoms. And this is defined by the set traces phi is defined by traces phi is the set of all such words such that A1, A2, A3, so these are all sets of atoms, A4, ... all those words such that A1, A2, A3, A4. So this word is a potential, arises as, so can arise as the trace of pi for some pi such that pi satisfies phi. So in other words, it's the set of all possible traces, that is, infinite words whose symbols are sets of atoms, of traces that can be the traces of paths that satisfy phi. Okay. So I'm going to comment in red that actually it's also possible to define, so let's put a little blob here. it is possible to define traces phi directly by modifying the definition of the satisfaction relation. So what is possible to do is to define the satisfaction relation directly between traces and formulas rather than between paths and formulas. So modifying the def of satisfaction and I shall put some slides on the web page that do that. They don't need to be part of the lecture. Okay, so we now have the traces of an LTL formula, and what we are going to show the remainder of this lecture the goal of this lecture is given phi, we're going to define a generalized non-deterministic Bucchi automaton, which we'll call A of phi, for which the language of the Bucchi automaton, of the generalized non-deterministic Bucchi automaton, goodness me, what a mouthful, the omega language, the set of omega words it recognizes, is exactly the traces of phi. So in other words, the criteria for a trace to satisfy a formula, so to speak, in other words, for a trace to be a trace from a path from a potential path that satisfies the formula, that criteria can be detected by a generalized non-deterministic Bucchi automaton, in that the generalized non-deterministic Bucchi automaton can recognize which paths can recognize exactly those infinite words over sets of atoms that are traces. Okay. So in particular, we have that the language traces of phi is omega regular, because it is a language recognized by a non-deterministic Bucchi automaton. For convenience, we use a generalized one, but of course we could, by our earlier proposition, convert it to an ordinary Bucchi automaton. Let's underline this, an ordinary non-deterministic Bucchi automaton. So, to simplify matters, we assume we're only going to use a subset of the connectives of LTL. So we're going to assume that phi uses only the following connectives, logical connectives. So we're going to use negation, disjunction, true, the next operator, and the until operator. So we don't have the future operator, the global F, the global operator G, the weak until operator W, and the release operator R. Instead, we also don't have conjunction and we don't have implication. We somehow know how to replace conjunctions and implications with combinations of these connectives. For the other temporal operators, so future, global, weak until, and release, we can also replace formulas involving them with formulas involving these. So there's going to be an exercise for exercise classes. Show that every LTL formula is equivalent to one involving only the above constructions. The above connectives only. Okay, so now henceforth, assume we are given a formula, an LTL formula by, oops, that's a bit off center, let's try again, phi as above. So namely using exactly these connectives. Of course it might have some propositional atoms in, otherwise it would probably not be very interesting. And what we're going to do is construct a generalized non-deterministic Bookey automaton, the generalized non-deterministic Bookey automaton A phi. So that's our goal. Our goal is to construct A phi. Okay, so the first thing we're going to do is define what the states of A phi are. So A phi is a Bookey automaton, so a generalized non-deterministic Bookey automaton, so we need to give the set of states, the transition relation, the alphabet is going to be the power set of atoms because we want it to define the trace language. Anyway, we need to define all the components. So to define the set of states, so the states are going to be sets of formulas. And the thing is, we think of the sets of formulas is that as a set of formulas that can be true at a given state in a run that we're trying to validate the formula over. So states will be certain sets of formulas. So firstly, we want to restrict to only a finite collection of formulas to consider as the formulas that can belong to the set of formulas that defines a state, because we only want finitely many states. So I'm going to define firstly a set of formulas that we're going to restrict attention to. So the complemented subformulas of phi, which we call CS phi, is defined by, well, let me write that later. So they're defined by, so the point of a complemented subformula is it consists of all the subformulas of phi, that's all the formulas that one can see inside the formula phi, and phi itself, and also their complements. So we can define that in the following way, that okay, so we're defining the set CS phi of complemented subformulas. So let's just say the set of complemented subformulas. So phi is a complemented subformula of itself because it's a trivial subformula of itself. So if some formula psi, if we've already got that it's a complemented subformula of phi, and it is not a negation, if psi is not a negation, then we put not phi also in the complemented subformula. So this is how we complement the formulas that appear in the complemented subformulas of phi, by adding their negations. So if we do have a negation, not psi in, so if we have a negated formula that appears in the complemented subformulas of psi, then we add psi to the complemented subformulas of phi. Okay, so these two work together to make sure that for every formula, it and its negation in some form appears in the complemented subformulas of psi. And also then if we have any complex formula, so if we have let's do that. Sorry. We do the same for if x psi is a complemented subformula of phi, then also psi is a complemented subformula of phi, because if this is a subformula, then psi is also a subformula. And then if we have any binary connective, so if psi or psi prime, let's have a look at what connectives we're looking at. Well, true is just true. We've already dealt with not and next, so with the two binary connectives are or and until, let's put them together. So if a disjunction is a complemented subformula or an until, I realise there's a bit of a danger having both disjunction and until, because if you don't write them carefully, they can look like each other. So let's make a very sharp disjunction there, and we'll make also and we'll make a very nice round until. So if either of those belong to the complemented subformulas of phi, then in which case both psi and psi prime need to be complemented subformulas. Then and psi prime are both complemented subformulas of phi. Okay, well that took a little bit of writing. It's quite abstract, hopefully not too hard to understand. So let's have a look at an example which will help us. So if we look at the complemented subformulas of the formula A until B, then it's the set. So we're looking at the complemented subformulas of this subformula. So intuitively, it's the set of all subformulas together with their negations. So the subformulas are A until B, A, which is of course a formula because it's an atom, and B. So there are three subformulas, and their negations are not A until B, not A, and not B. So we have 6 elements in the complemented subformulas. So we can see this, we can get this from the rules, because firstly, the formula itself belongs to the complemented subformulas. So we need to put A until B in there. Once that's gone in, then it's not, so psi is now A until B. It's not a negation, so its negation goes in. So we have not A until B goes in. So not A until B is in, so by this A until B needs to be in, but it already is. From A until B being in, because of this, we have that both A and B belong to the complemented subformula. So we have A and B. And then again by the clause about negations, so putting psi here to be firstly A and then secondly B, then negations also go in. And that's the end of the complemented subformulas. We don't get, by applying any of the other rules, we don't get any more formulas. And one can easily construct this algorithmically. Okay, so let me just remark, states will in fact be certain subsets of the set of complemented subformulas of phi. So which subset? So for this we need another definition. So it's rather intense, this lecture, quite a lot of definitions. So a subset, so a subset of the set of complemented subformulas of phi. So a subset of the set of complemented subformulas of phi is elementary if it satisfies some properties. And the point is, these elementary sets are going to be the ones that, the elementary sets are going to be our states, and the states of the Bookie automaton that we're constructing. And the formulas in the set here, the idea is they are formulas that hold simultaneously at a state in the transition system, well, a state on the run that we're looking at, rather. So they're sets of temporal formulas, of LTL formulas, that can hold at the same state in a run, a longer run. So we're going to see some conditions there, and we want to make sure we also put in every formula from the complemented subformulas that holds at a given state. So let's look at the conditions and we'll motivate them as we go along. So for every formula or let's say for every negated formula, either the negated formula belongs to S or psi belongs to S, but not both. So the point here is the set we're defining, the set S, is the set of formulas that are true at a given state. And so at every given state on a run, either psi will be true or not psi will be true, but of course it won't be the case that both psi and its negation are true at the same state along the same run. So we can never have a formula with its negation, but one of them should be there, because one of them will have to be true. Also if we have psi, if we have a disjunction, and it belongs to the state S, well, if a disjunction is true, psi or psi prime is true at the state S, then that means either psi is true or psi prime is true. So one of these must belong also to the state S if we want S to contain all the formulas from the complemented subformulas that are true. So if this belongs to S, then in this case, so psi belongs to S or psi prime belongs to S. In this case, it is allowed to have both. So at least one of the two formulas must belong also to the state S. Also, if the true formula belongs to the set of complemented subformulas of phi, then true is of course true at every world. So if it's one of our allowed formulas, we only consider S is a subset of the set of complemented subformulas, so we're only allowed to put true in if it belongs to the complemented subformulas, but then it should belong, if it does, it should belong to every state. So then true belongs to the state S. So the last two conditions are about the until operator. So if psi prime belongs to the state S, well, if psi prime is true now, then for any formula psi until psi prime is true, because remember, until trivially holds if the second formula in it is true at the moment. In general, psi until psi prime is true if psi keeps on holding up until the moment before psi prime suddenly holds. But if psi prime holds now, then we don't have any requirements on psi. So we're going to, so if psi prime belongs to S, then as long as whenever we have a formula, psi until psi prime belonging to the set of complemented subformulas of phi, then that should belong to S. So this is, sorry, psi until psi prime belongs to S. And another condition in the other direction is that if psi, let's make that until a bit bigger, if psi until psi prime belongs to S and psi prime does not belong to S, so now we're in the case that psi until psi prime belongs to S, so it is one of the complemented subformulas of phi. So this until property is true at S, but psi prime does not belong to S, so psi prime is not true at S. Well, in that case, for an until property to be true, but the formula that we're waiting for it to be true, eventually the psi prime, if that's not true now, then for the until property to be true, then psi itself, the first formula, needs to be true. So in this case, we need to require that psi, which is, of course, one of the complemented subformulas of phi, because the whole until formula is, so this then needs to belong to S. And those are all the conditions. So, again, if we look at the elementary subsets of the set of subformulas of A until B, so these are, and now, well, we can just enumerate what they are. So we can have A and B, and if we have B, then we have to have A until B. I mean, with the propositional atoms, you can, in general, have any combination of them or their negations consistently being true or false. There are no restrictions on the propositional atoms, but if A and not B hold, so if we look at the different propositional atoms, then we see what is forced for the other formulas that are in the complemented subformulas, which are just A until B and the negation of A until B. So if A and not B hold, then that, again, A until B can perfectly well be true. Has to be true. No, it doesn't have to be true, but it can be true. We can also have A and not B. It doesn't have to be true because we can also have a not A until B. Right, so sorry, I was misleading when we talked through this case, because A can be true and not B is, and not A and not B can both hold, but we don't have to have A until B, because it's possible that we might then go to another state in which, for example, we might then go to the next state in which not A and not B both hold, in which case it's clear that we didn't have A until B. So it's consistent for not A until B to be together with A and not B. It's also consistent for A until B to be together with A and not B. The point is that this condition gave us that if we have A until B and we also have not B, then we're forced to have A. So we're not going to have A until B, not B, and not A, for example. That will not occur. So we also have not A and B. And because we have B, we have to have A until B. And we can also have not A and not B. And then we're not allowed to have A until B with this. because whenever we have A until B and not B, we have to have A by the last condition here. So in this case, the only possibility to go with this is not A until B. And so those are all the 5 elementary subsets. Okay, so now let me tell you again. So the states of the generalized non-deterministic Bookey automaton are the elementary subsets of the complemented subformulas of phi. So now we need to define the transition relation, and I'm just going to define it. So A here is a set of atoms, and S is a state of the generalized non-deterministic Bookey automaton, so it's an elementary subset of the complemented subformulas, so is S prime, and this holds if and only if, firstly, A is exactly the set of atoms in S, and maybe I'll put the and up here. Now the point is, we want to say we have a transition if it is legitimate, given the properties that hold at S, for us to move to a state with properties S prime as the next step. So we should also have then that whenever we have, if we're moving to S prime as the next step, so then whenever we have X psi, if we ever have a formula next psi in S, well then psi needs to hold in S prime, because the point is we're viewing this as the next step in our run. So this implies that psi belongs to S prime. And similarly, if it's not the case that next psi holds in S, well then we want that not psi belongs to S prime. Because if psi were true at S prime, then next psi should have been true at S, whereas we've got not next psi. And from the rules on elementary complemented subformulas, if not X psi is a complemented subformula of the original formula phi, then not psi is also a complemented subformula. And then some more. So and let's go leave a little bit more space. So if we've also got that psi until psi prime belongs to S, and not psi prime belongs to S. So in this case, psi until psi prime was holding at state S, but we hadn't yet got to psi prime. So that means when we go to the next state, psi until psi prime must still be holding. So these two conditions imply that psi until psi prime must belong to S prime. And furthermore, if we have the negation of an until, so if instead it's not true that psi until psi prime, if that belongs to S, and if psi belongs to S, then we better make sure then in that case it had better be the case that it's not true that psi until psi prime holds at S prime. Because if psi until psi prime held here at S prime and psi held at S, then that would mean that psi, then as we're going into S prime on the run as our next step, that would mean that psi until psi prime would also hold at S, but we've got that it can't hold. So we see that the negation of an until needs to propagate forwards in this way. So it's a little bit complicated, but now we can start to draw our Bookey automaton. So we had our 5 elementary subsets, and let me draw them in a sort of nice arrangement. So we can have not A, not B, not A until B. We have not A, B, A until B. We have A, not B, not, I suppose I should put the brackets round, but not A until B. We have A, B, A until B, and we have A, not B, A, not B, and A until B. So we don't have any nexts to take care of, so the only conditions that are important for the transitions in our Bookey automaton are these ones, that if you have an until and the negation of the second formula, then you propagate the until forwards, and if you have the negation of an until and the first formula unnegated, then you propagate the negation forwards. So here we have here, for example, we have an until and the negation of the second formula. So we propagate that. So that will go to here, for example, because the until is being propagated forwards, and it will also go to here. And similarly, if we have a negated until and the first formula, then we propagate them. Then we can propagate the negated until. So if we have a negated until and the first formula, as we do here, then that will go to any place that has a negated until. So that goes to here, and it also goes to itself. And I forgot to do that this one goes to itself. And, well, one could spend quite a bit of time working out all the cases, but let me just complete the picture. But it's a very good exercise to do this for yourself. This, in fact, goes both ways. So as does this. Here we have a loop. Here we have a loop. This also goes both ways. There are arrows like this. This also comes down to here. So as you see, if I talked you through it, it would take rather a long time, and we've already actually used rather a long time in this lecture, so I don't think you want me to talk you through it. And finally, there's an arrow going all the way down from here. Right, I think we are done. One little thing missing. Oh, we've got another self loop here. So all these states have self loops in this case. One thing missing is I didn't put the labels on. So if I was putting the labels on, then the label is just the set of atoms from the start state. So for example, if I was putting the labels on here, this transition would be labelled with the set A not B, or rather, sorry, it's just the set of atoms that are true, so this would be labelled with the set. Let's be strict about it. So this would be labelled with A. Now the picture would get a bit complicated if we wrote these labels, because in this direction from here to here we would have the set A, or maybe let's just do it in that case, and then we'll leave the rest to just be implicit. So in this case we have this arrow, this has the set singleton A, because that's what's true at the start state of that transition here, and going in the other direction we have the set AB. Anyway, and I was writing those in blue, so let's be a bit consistent. Sorry. So A, AB. Okay, so here's our generalized non-deterministic Bookey automaton. It's not quite finished because we've got the states, we've got the transitions, we still need the start states. Oops. So the initial states is all those elementary sets of formulas of complemented subformulas S that contain the original formula psi. So in our case, phi was A until B. So the start states are the three states that contain A until B. Not the negated A until B, but actually A until B. So we just normally denote start states. Let me write a different colour there. So let's have purple arrows in for the start states, just to... Okay, so the start states, you just have an arrow coming in. And we need the final states. But this is a generalized This is a generalized non-deterministic Bookey automaton. So for the final states, we don't just have one set of final states, we have several sets of final states. So let psi1 until psi1 prime to psi k until psi k prime be all until formulas in the set of complemented subformulas of phi. So depending on how many different until formulas there are in the set of complemented subformulas of phi, we have that many sets of final states. So for every such formula, we define fj. So for every such formula, let's call it psi j until psi prime j. 1 is less than, so j is between 1 and k. So it's one of the until formulas. We define the final set to be all those elementary sets, so namely states of the generalized Bookey automaton, such that either the right-hand formula of the until belongs to the set, or the negation of the until belongs to the set. So, or the negation of the until so in our case, we only have one. If we go back to the complemented subformulas, we only have one until formula, that's A until B. So we only have, so actually in our case, in our example, we only have one set of final states, so we get a Bookey automaton in our case. And the final states are the ones that contain the negation of that until, so not A until B, so it's this one and this one, or those that contain the second formula in the until, the target formula of the until. So that contain B. So these ones contain the negation of the until, and these two contain B. This one contains neither. So we have one set of accepting states, and it contains 4 states. So let's again use green for the accepting states. So this one, so let's ring them in green. This one because it's negation of an until. This one because it's the negation of an until. This one because it's negation of an until. And this one because it contains B, the target formula of the until, and this one also because it contains B. And there is our Bookey automaton. And in general, we get a generalized non-deterministic Bookey automaton. In our example, we obtained actually just an ordinary non-deterministic Bookey automaton. Because we only had one until formula in the set of complemented subformulas. The idea is then that the language defined by this automaton will correspond exactly to the language of traces for the formula A until B. So we can kind of see that in this case by thinking about what would it mean for an infinite path through this not to be accepted. Well, an infinite path through this will be accepted, so a run through the automaton will be accepted as long as it goes through a final state, some final state infinitely often. So for a run not to be accepted, it means that we'll have to go into this state and stay here. And when we get into this state and stay here, we see that A is true, but B will never become true. So if we go into this state and stay here, then we do not validate A until B. So maybe a better way of thinking about it is that the accepting runs through the automaton are those runs that do visit final states infinitely often. Those runs will always, at every stage, validate every formula in the set, every formula in the set of formulas at the state. So we can never get stuck in this state, because if we got stuck in this state, we would be invalidating the A until B formula. Okay, there's been quite a lot of material in this lecture. We've done now the hard part of the work. It's really quite complicated, but when you get to appreciate it, the Bookie automaton is a little bit of a fiddly construction, but it's really very impressive what this machinery is doing for you. At least I find it so. But anyway, I think that's more than enough material for this week. So that completes 2 parts of the algorithm that will perform the model checking problem for LTL, and the next and easier final part will be next week, together also with then some applications of it. Okay, so that's it for this week. Bye for now.